I will talk about isoperimetric inequalities for subgroups of products of free groups from a joint work with Bertolotti, Italiano, Iosa-Isenrich, and Migliorini. And so what I will do is first I will briefly introduce the Dehn function, like recall the main facts about Dehn functions. Then I will talk a little bit about subgroups of direct products of free groups. And then I will state, let's say, our main results. And in the last 2-3 minutes, I will give an introduction to one of the ideas that are used in the proof. So Dehn function. Let's start with a finitely presented group, so generators x1, xn, and relations R1, Rm. And let's take a word W in the free group over these generators and suppose that W represents the identity element of G. What does it mean? Since G is the quotient of the free group by the normal subgroup generated by R1, Rm, this just means that W can be written as a product of conjugates of our relations, okay? And we define area of W as the minimum K such that W can be written as a product of K conjugates of relations. Okay, so we are trying to write W as a product of conjugates of relations, and we are trying to use as few relations as possible in order to do this. And this is the area of our word W. Let's say, just roughly speaking, the area measures the complexity of certifying that W represents the identity in G. Okay. The reason why it's called area is that this has a geometric interpretation. So let's consider X to be the presentation complex for our group G. So a CW complex with one vertex and one cells corresponding to the generators and two cells glued according to the relations. And let's also consider X tilde to be the universal cover of X. So the one skeleton of X tilde is just the Cayley graph of G with respect to this set of generators. And then you have cells. For every cell, you have all of its translates glued on X tilde in order to make it simply connected. Our word W that represents the identity in G can be represented as a loop inside X tilde. So you read the word W and you start at the base point and you move along the edges of the Cayley graph accordingly. And since W represents the identity, you will go back to the base point. And writing W as a... Okay, so since X tilde is simply connected, this can be filled to a map from the disk to X tilde, okay? So we can complete this to a map from the disk to X tilde. And let's say, without going into any detail, this can be done in a sort of simplicial or CW way. So you can subdivide your disk in a way like this, and the map sends each of your polygons to one of the disks corresponding to some of the relations. So for example, maybe this triangle is sent to this two cell here, okay? And this corresponds to writing W as a product of the suitable conjugates of the relations that are used in the filling disk. And the area in this case is how many two cells the disk goes over, okay? How many two cells are covered by our disk. So if we choose, there are many possible choices for the disk. And we are looking for the disk that passes over as few two cells as possible. The area is really a geometric area where every two cell is given area 1. Okay. And with this, we can now define the Dehn function of a group. So we fix a certain number n, and we take all words W of length up to n, representing the identity of G. And for each of them, we compute the area, and we take the maximum of all these areas. So it's the worst case possibility for the area. And this, as a function of n, this is called the Dehn function of our group G. In principle, the Dehn function will depend on the presentation. But in practice, we are only interested in the large-scale growth of the Dehn function. So for two functions, f and g from n to n, we say that f is asymptotically smaller or equal than g if for some constant c, this inequality holds. And we say that f is asymptotically equivalent to g if the two inequalities hold. And what happens is that in different presentations for the same group will give asymptotically equivalent Dehn functions. Okay, so the Dehn function is defined up to asymptotic equivalence. In particular, it makes sense to say that a group has linear Dehn function or quadratic Dehn function or cubic Dehn function and so on, okay? So the polynomial is not uniquely determined, but the degree of the polynomial is. The Dehn function somehow encodes the complexity of solving the word problem in the group G. For example, G has solvable word problem. So there is an algorithm that tells you whether a word represents the trivial element of G, if and only if the Dehn function is recursively bounded. Recursively bounded means bounded above by a recursive function. A recursive function is a function which is computed by a Turing machine. Okay? And the groups with easiest possible word problem are exactly the hyperbolic groups. So the Dehn function is linear if and only if the group G is hyperbolic. Otherwise, the Dehn function is at least quadratic. Okay, so there is a gap. Okay, the easiest groups are the hyperbolic ones. And besides that, everything is at least quadratic and there's nothing in the middle. Above quadratic, there is like a lot of possible Dehn functions. Okay, so this is any questions so far? Okay, so now let me introduce the second main character of our talk, which are subgroups of direct products of free groups. And well, one thing that had already been observed is that F2 cross F2 is infamous for having a lot of subgroups that can behave in very ugly ways. So for example, if you look at all subgroups, you have uncountably many isomorphism classes of subgroups. And if you restrict your attention to finitely generated subgroups, you find some with unsolvable membership problem and some with unsolvable conjugacy problem, for example. But there is a surprise here. If you restrict your attention further, going to only finitely presented subgroups, then all finitely presented subgroups of F2 cross F2 can be classified, and actually the classification is quite easy. If H is a finitely presented subgroup of F2 cross F2, then H is virtually a direct product of free groups. So each H is up to finite index is itself a direct product of free groups. I will talk a lot about direct products of free groups. I always mean finite products of finitely generated free groups. So finitely many factors and finitely generated free groups. And this result can be generalized to products of more than two free groups. And the result is the following. If H is a subgroup in a product of n free groups, and if H is of type Fn, then H is virtually a direct product of free groups. What does type Fn mean? Here, let me recall very quickly the definition. Type Fn means that there is a kH1 with finite n skeleton. In particular, say for two factors, type F2 means there is a kH1 with finite 2 skeleton, means that H is finitely presented. So as a particular case, we recover this other theorem. Okay. But for example, for 3 factors, this only gives us information about the subgroups of type F3, so not all finitely presented ones. And for a higher number of factors, you get only information about subgroups with higher finiteness properties. And it is possible. So let me show, first of all, an example of some other subgroup that you can find in a product of n free groups. So take a product of n free groups of ranks m1, mn. M1, Mn are all required to be at least 2 and at least R. At least R because now we are taking a map to Z to the R. And what is this map? Well, if Fm1 is generated by A1, AR, AM1, A1 is sent to E1. E1 ER is the basis for ZR. We send A1 to E1, AR to ER, and the other AR plus 1, AM1, we send all of them to 0. Okay? And similarly, if Fm2 is generated by B1, BM2, B1, BR are sent to E1, ER, and the others are sent to 0. Okay, so let's consider this specific map from this product of free groups to Z to the R, and define K, M1, Mn, R to be the kernel of this map. Okay, so clearly this is a subgroup of a product of n free groups. What is not trivial is that this subgroup is finitely generated, finitely presented, even better. It's of type Fn minus 1, and it's not of type Fn. Okay, so it's so this is one of the subgroups that lie in the middle. If you from finitely presented to type Fn, there is a lot of finite properties in the middle. If you go down one step from Fn, you find these subgroups of type Fn minus 1. And here we have another surprise. These are all of them. So if H is a subgroup of a direct product of n free groups, and if H is of type Fn minus 1, then H is up to finite index isomorphic to one of these, or to a direct product of free groups, of course. Okay. And this is a result that was proved, technically it's Kropoller and Josa Isenrich, but it's based on the work of other people before them, so I preferred to cite them all. So there is a classification theorem for subgroups of type Fn minus 1. There is also a more complicated, in particular, for 3 factors, this classifies all finitely presented subgroups, okay? In a direct product of 3 free groups, you have finitely presented is the same as type Fn minus 1 for n equal 3, okay? But for n, for 4 factors, 5 factors, more factors, there is a similar classification theorem. I will not go into the details of that. Let's just say that it becomes very, very messy very, very quickly. In particular, instead of taking kernels, you have to take pullbacks, and you have to iterate this construction. So not just taking kernel once, but taking kernel several times, taking pullbacks several times. And you need to use maps to nilpotent groups instead of to free abelian groups. But this led people to the following conjecture, because nilpotent groups have polynomially bounded Dehn functions. And looking at this construction, Bryson stated the following conjecture, that if H is a finitely presented subgroup in a product of free groups, then the Dehn function of H is polynomially bounded. Okay, this is still open. This is the conjecture. Actually, and let me go over this very quickly. For people that already know stuff about limit groups, this is equivalent to another conjecture that for every finitely presented residually free group, its Dehn function is polynomially bounded. This is a very interesting conjecture because this is a big class of groups. So we would find a big class of groups with polynomially bounded Dehn functions. And the reason why the 2 conjectures are equivalent, it's not too hard to prove. It's because residually free groups embed into a direct product of limit groups. And limit groups are similar to free groups. They have quadratic Dehn functions. And so from one conjecture, you can deduce the other. Okay. Okay, so let me tell you what is known about the Dehn functions of these K, M1, Mn, R. So for now, we are only investigating the Dehn function of subgroups of type Fn minus 1 in a product of n factors, because the others seem, well, for now they look very complicated. But for these ones, the first observation, well, it needs proof, but it's not too hard again, it's a lemma, is that the Dehn function doesn't depend on the values of m1 and n, provided that they are bigger or equal, of course, than r and then 2, okay? So, for example, if r is equal to 1, we can set all the mi's to be equal to 2, and we only care about the group K, 2, 2, 2, 2, 1. These are called the Stalling-Sbierri groups, and it has been proved reasonably recently that the Dehn function are all quadratic. Okay, so now we focus only on the case r bigger or equal than 2. Again, since the Dehn function doesn't depend on the specific values of m1 and n, we only care about k r r r r, which we abbreviate as k n r, n factors of rank r. Okay, and for this, Dyson already proved a polynomial upper bound, which is the following. Notice that, so for in a n factors rank r, you have a bound that depends only on r and not on the number of factors. But the problem is that, yeah, the dependence on r is a problem because, for example, if you are looking at all finitely presented subgroups in a product of 3 factors, and this doesn't give a uniform upper bound on all of them because for every R, there is one subgroup in a product of 3 free groups associated with that rank R. And also, Kropoller and Jose-Heinrich proved that these Dehn functions are quadratic, provided that n and r satisfy a certain inequality, which is, roughly speaking, we are saying that number of factors bigger or equal than 2r. And also Dyson had a result about the specific group K32. He proved that the Dehn function is at least n cube and at most n to the 6. Okay, but at least n cube. So we have a non-quadratic Dehn function here. And we improve all these 3 of these results. For example, in a product of 3 free groups, we prove that for every r, the Dehn function is bounded by n to the 9. Okay? So in particular, this tells us that all finitely presented subgroups in a product of 3 free groups have Dehn function bounded above by n to the 9. And for 4 factors, we have a uniform upper bound of n to the 5. And for at least 5 factors, we have a uniform upper bound of n to the 4. Of course, for 4 or 5 or more factors, this is not all the finitely presented subgroups, but just the ones with finiteness type fn minus 1. And this result of Jose-Heinrich and Kropoller, we improve the inequality. So we prove it, they had already conjectured that it should hold for n bigger or equal than r plus 2. And now we are actually proving it. And finally, for the specific group K32, we have an exact computation. Okay, so we proved that K32 has Dehn function n to the 4. And oh, sorry. This is a mistake in making the slides, sorry. And okay, so just as I said before, this in particular is a result about all finitely presented subgroups in a product of 3 free groups. And I also point out that this is the first super quadratic exact computation of a Dehn function for groups in this class. Okay, other groups were known to be quadratic, like these ones, Stalling-Sbierri or these other ones. But here, like n to the 4 is harder to prove because for n squared, the lower bound comes for free because you just check that the group is not hyperbolic. But for n to the 4, you actually have to find a way to produce the lower bound. So in the last 5 minutes, let me give you, well, these results are all require several ideas to be proved. In fact, our paper is very, very long. So I will just, I just shows one idea and I will show it that. So I will talk about the upper bound. So I want to give you an idea of how this upper bound is produced. So let's take, for example, K3R, which is this kernel, okay? And you can, it's quite easy to prove that it has a certain set of generators, which we call X1, XR, Y1, YR. And I will not investigate more on what these guys are, but it's not hard. And so we are given a word W of XI, YI, which represents the identity of K3R. And we want to find a filling for W. And what we do is the following. First of all, we take FR cross FR cross FR, which is represented by this sphere. And so this represents the Cayley graph plus the two cells glued, okay? And we represent ZR as a line, okay? I realize that it's not a line, but for simplicity, let's represent ZR as a line. And this map is a map from the Cayley graph to this line. So think of it as a height function, okay? For every point in the Cayley graph of FR cross FR cross FR, this tells you at which height the point is situated. And consider K3R is the kernel of this map. So it's the points which are at height 0. So you should think of it as a level set of this map. Okay, so take your sphere and cut it with a plane, and this circle is K3R. Okay, our word W is a word that lives inside K3R. It's written in the generators of K3R. The generators of K3R, by definition, they don't change the height at which you are. So this word W, roughly speaking, can be represented as a loop living inside this 0 level set. Okay? And what we do is it's easy to fill it inside the product of 3 free groups. So we fill it with a disk inside the product of 3 free groups. Okay? The problem is that this disk is not contained in the kernel, but instead along the disk the height changes. So the disk goes up and down. Okay, inside this ball. And so we use a technique called push down to push down literally this disk to a disk contained in K3R. Okay, so this is more or less how the upper bound is obtained. You start with a filling in FR cross FR cross FR, and the Dehn function of this guy is quadratic, so you do this using n-square relations. And then you push down this disk to be contained inside the kernel. I'm not going to describe how this push down works exactly, also because the formal proof is completely algebraic, even though the idea is geometric. What you obtain is a filling of your word inside the kernel, but the problem is that this filling is not obtained using relations of K3R, but it's a filling made using more complicated words, which we call thick relations. And so one has to explicitly explain how to fill these thick relations using the actual relations of K3R. So this is, roughly speaking, how the proof goes. And this is more or less everything I wanted to say. So thanks for the attention. I think, yes, time is more or less over. Do people have any question?
Okay, let's thank Dario for his talk. As he said, any questions?
Could you spend a few words why you get like the exact exponent 9? Like you start with a quadratic covering.
Yes. Unfortunately, this is essentially technical in nature. So in practice, you perform this push down. As I said, you find some filling, but this filling, like you write W as a product of conjugates of thick relations, and you want to write it as a product of conjugates of relations instead. So you write down these thick relations, they are certain words, you write them down, and then you explicitly show how to fill them. And when we explicitly show how to fill them, we use n⁷ relations in the worst case.
Okay.
And so you have n² thick relations,
I see.
and each of them is filled with n⁷. But how this n⁷ appears, it's just by hand you fill the word, and you need that amount of time to do that. Like it's
Mhm.
just that it comes from the technical computation. I don't have an intrinsic reason for this. And also, I want to point out that we don't know, because otherwise we would have written in the paper, but we suspect that this is not optimal. So probably n to the 9 is not the best possible upper bound, but it can be improved probably to at least n to the 7, n to the 6, or something like that. Or maybe even to n to the 4 for all of them. But this is not clear.
And it gets easier once you have like more factors,
Yes,
right?
How yes.
So?
This is a thing. Well, yes. On one hand, it gets easier because somehow having more factors gives you more space to move and helps you while doing the filling. On the other hand, you are not dealing with all finitely presented subgroups, but only with the ones with a certain finiteness property. So, yeah, I guess if you take, yeah, where is it? Here, like we are only doing this K and R. But if you go to lower finiteness properties, you find many more subgroups, and we don't know about their Dehn functions.
I see.
And we don't know even the presentations.
I see. Thank you.
Yeah.
Okay, are there any more very quick questions since we started this talk 2 minutes late? Okay, if there are no more quick questions, I guess we'll thank Dario once more.